Brian is particularly interested in the cyclic economy, and I think he will perhaps tell us a little bit about that also, about the reclaiming of materials, perhaps particularly metals, from discarded materials. So Brian, before he became involved with Brunel, was Vice-Chancellor of the University of Bradford, and before that, the University of York. While at Bradford, he created the World Technology Universities Network, which he continues to chair. He's also an editor of Elsevier's premier review journal, that's Progress in Materials Science. And he's published over 300 books and papers. He has been mentioned a trustee of the Science Museum group, and a very helpful and experienced trustee too. So he's won numerous academic prizes. He has a number of honorary professorships and fellowships in the UK, USA, China, and India. He was awarded a CBE, Commander of the British Empire, for services to higher education in 2013. So, Brian, it's a great pleasure for me to invite you to give your talk on the topic of high entropy alloys, the so-called Cantor alloys.
Okay, well, thank you so much, Mary, for that very, very kind and nice introduction. It's great to hear things from a colleague like that. I feel embarrassed, of course, a little bit, but that's part of the point. Hi, I can see Professor Badisha has joined us. Hi, Harry, good to see you. I'm just about to start. And let me just thank Fabio Maini, Professor Maini, also for inviting me to give this talk. It's a great pleasure to do so, and I'm sorry. Right, so, well, welcome to everybody to this lecture. Sorry about the starting difficulties. And thank you again very much to Dame Mary Archer for introducing me, and for Fabio Maini, Professor Maini, for inviting me.
It's an honor.
So, as Mary said, my name is Brian Cantor, as it says there. I'm a professor, emeritus professor at the Department of Materials at Oxford, and a research professor at an institute called BCAST in Brunel University in London. And I'm going to talk about multi-component high entropy alloys, and one particular group of those, which are called Cantor alloys, named after me, as Dame Mary has already said. And I've got three messages I want you to take home. The first one is that human history is the history of the development of new materials. All human developments have been driven by the development of new materials. That's not widely known, but it's very important. Second thing is that all materials that we use are alloys. What are alloys? They're mixtures of other materials. We call them, the individual starting materials, components. So all materials that we use are mixtures of other starting materials, components, which means that they are all alloys. So we use I'm going to use the two terms more or less equally, materials or alloys. And the third point is that there are gazillions of materials. The word gazillions is not a technically accurate term. It's not used, there's no definition of what gazillion means. But I will give you a definition when we get later. There are lots of them. And that's a very important take-home message, many more than might reasonably be understood. So I'm going to first of all start with a brief history of the world and materials, the human world. So 4 million years ago is the beginning of the last ice age. That's also when humans emerged from apes. We evolved from apes, almost the same time. And almost the same time is the beginning of the Stone Age, the age when humans, the first humans that just emerged, began to use flints and stones that they found as tools. These things are all linked. The poorer weather meant that apes found it harder to find food when they were just foraging for plants or trying to hunt for animals. And it became advantageous in evolution terms for humans to emerge with bigger brains and to begin to use tools in order to be more effective at gathering the plants and hunting the animals to get the food. So these things are all linked, and they're all driven by the discovery of a material, flint, a natural material, flint and stones, to be used as tools. And flints are an alloy. They're an alloy. All rocks and all minerals are actually alloys of oxides. And I'll say a word or two more about that in a second, but they are mixtures of oxides. Flints are mostly silicon oxide with a little bit of calcium and iron oxide added as well. The next thing that happens is a lot later. So most of the last 4 million years was the last ice age. 99.7% of the last 4 million years, we were in the ice age. Humans had emerged, and they were using flints as tools to get their food, whether cutting down plants or hunting for animals. And then about 12,000 years ago, about 10,000 BC, something important happened. It's called the agricultural revolution. Actually, what really happened is it was the end of the ice age. The end of the ice age is about 12,000 years ago, just 0.3% of the time since the ice age started. And of course, the weather warmed up, and it became easier to settle down in villages and to begin to farm, and to farm plants and to farm animals, to domesticate plants, domesticate animals. It's a massively important development. It's often regarded as the most important change in human circumstances occurred since humans appeared, the agricultural revolution. But you know, it was driven also by a material development. Humans discovered how to fire clays by heating them getting the right mix and heating them in a fire, so that you could make bricks for the houses that people began to live in, and they could make clay pots to store the food that they'd farmed. Without the houses and without the storage capability, it would have been no use trying to settle down and have an agricultural revolution. The material development was at the heart of it. And once again, clays are alloys. They're basically aluminosilicates, which are again mainly silicon oxide, with amounts of alumina, aluminium oxide, and some other oxides added too. And getting the right alloy is absolutely critical to the development. So we jump forward now another 6,000 years. That's half the time since the beginning of what's called the late Stone Age, when we had the settling down of people into villages. And people then discovered by accident that you could remove the oxygen from the oxides and get metals. This is a process called smelting. If you heat oxides, all the stuff we find, the soils, the rocks and so on, are mixtures of oxides. If they're heated in the presence of carbon, and we use carbon in the wood that we use to make a fire, if the ore is mixed, if the oxides are heated in the presence of carbon, then they're what's called smelted. The carbon reduces the oxygen, and the metal is produced. The basis of the oxide is removed, and you get the basis itself, which is the metal. That's how the Bronze Age began. Now, initially, people discovered that you could do this by accident, by lighting fires on top of the appropriate oxide ores, and they discovered tin, and they discovered lead, and they discovered copper. But these metals, when they're pure, are very, very soft, and they were not very usable. They were used just for ornaments. And then somebody made the discovery that if you added a little bit of tin to copper, which doesn't happen very easily naturally, it took a while for people to discover it, you get what's called a bronze. It's an important alloy, copper with a few percent tin. I'll say a little bit more about it in a second, but it's a much better material than stone. You can shape it, you can make much stronger tools, and it helped for the development of the next stage of human development, which was the development of much stronger based villages and then even cities. And with the Bronze Age, we see the rise of all the very famous civilizations that we know about. The Minoan civilization in Crete, the Shang dynasty in China begins with the Bronze Age, the Mayan civilization in America, the pharaohs and the Greek civilization all relied on the development of the Bronze Age and bronzes. Now, another 3,000 or 4,000 years later than that, around about between 1000 and 2000 BC, the technology of the development of smelting, the kilns and the furnaces and the fires used to make these alloys got better, and suddenly people discovered they could make iron. Iron has a higher melting point than copper or lead or tin, and you need a much better fire. So there was an important technology development to get better fires. I'll show you a picture of that in a second. And that allowed iron to be smelted, which is a much better material. And iron absorbs, unlike copper, it absorbs a little bit of the carbon from the wood that's doing the smelting, but it absorbs a little bit and it makes it into what's called an iron, wrought iron and cast iron, and we then have the Iron Age. That led to the fall of all of those famous civilizations and the rising of new civilizations which were able to make use of these irons. That's when the Roman era begins. It's when China itself emerges from the initial dynasties. There's a whole series of changes in which dynasties are important, all linked to the development of an important alloy, iron, wrought iron and cast iron. We jump forward to the 17th and 18th century, which is the Industrial Revolution. Now, by a peculiar quirk of history, irons are alloys of iron with about 1, 2 or 3% of carbon. Steels are actually pure iron, just by a bit of irony, to use another word, it's a pun. So steels are iron with less carbon in them. They have about 0.1, 0.2, 0.3%, or maybe point something percent carbon, just a fraction of a percent of carbon. And the ability to manufacture steels was not really discovered until the mid 18th and through into the 19th century, and that's what actually drove the Industrial Revolution. So the Industrial Revolution begins with the scientific revolution, of course, in the 15th, 16th, and 17th centuries, which started in Italy with people like Leonardo and Galileo, and of course Britain was very important with the philosophy of Bacon, and then later the Newtonian mechanics and the Copernican revolution. So that's the scientific revolution. That is what led to the development of machinery for producing things for us in the mid-late 18th century. And it gathered steam through the 19th century. And it was the discovery of steel which allowed it to happen. What did the Industrial Revolution do? It led to the machinery, machines, engines, textile machinery, printing presses, and then later transport, things like railways and cars and planes and all those sort of things, and also the ability to build much bigger buildings by using steel as a construction material. So steel was massively important in driving all these things because you couldn't have the degree of precision with a rather poor quality material, which is wrought iron and cast iron. It was used, but it wasn't until we got steel that we were able to make things much better. And we had to discover how to remove some of the carbon to get us to a much smaller amount of carbon and control that to get all the properties we need. I mentioned very briefly jet engines. Jet engines were first proposed by in the 1930s by a man called Frank Whittle. He proposed them to the Ministry of Defence, who turned it down on the grounds that they said, we're not going to develop jet engines. There's no material which can withstand the heat of a jet at the centre of a jet engine. But again, another irony, the International Nickel Company that very year patented, this very same year that it was turned down, the idea, patented nickel alloys, which later are known as nickel superalloys, which are nickel with a little bit of aluminium and titanium to give them strength, and nickel itself provides the high temperature, important alloys, so because of that though, because of the turning down, jet engines didn't really get going for aeroplanes until the 1950s and 1960s. And of course, we finished with the second most important revolution in human affairs after the agricultural revolution was the Industrial Revolution of the 18th and 19th century. And the third most important, maybe the most important in the end, because we're still in it, is the Information Revolution. And that is, of course, based on silicon chips. And silicon is a semiconductor discovered. Its important discoveries were made in the 1950s and 60s. If you dope it, and doping is just alloying, microalloying, with small amounts of phosphorus or boron or nitrogen, or aluminium or some other things, you get these wonderful electrical behavior, which is so controllable that we get all the wonderful computers, telecommunications, and the internet and everything else that we're so familiar with, all based on the discovery of how to make these very, very finely controlled silicon alloys. So I'm hoping I've persuaded you with all of that the history of humans is all based around the development of important new materials. I'll just show you some quick pictures, just to put a bit of substance to all of that. And there's a flint chopping tool from about 2 million years ago, a very early tool. The earliest was the older one type. And a bronze dagger from about 1500 BC from Cyprus. It's oxidized, so it's green. This is a copper smelting hearth on the left. You can see it's just really like a fire, like a campfire almost. But this was used to smelt copper, putting copper ore into that. As the fires got better and we put chimneys on the fire, as shown in this this very nice picture painted on a pot from Greece, you can see this. This is how they began to get better quality fires, and this is what led to hotter temperatures and allowed iron and wrought iron to be made. You can see a blacksmith here pulling out of the fire some rather poor quality wrought iron, and he's going to hammer to make it a little bit better. In the Industrial Revolution, we have steels. Steels, if you have 0.8% carbon, then the steels have this alternating mixture of pure iron, nearly pure iron, and an iron carbide called cementite, Fe3C. And this, when it's hammered, produces these beautiful pictures on knives. It's called Damascus steel. That's quite a high carbon content for a steel. It's at the upper end of carbon contents, and that's a very high strength steel. But of course, the great thing about steel is, as well as having high strength, it can be molded into and shaped. And so you get these absolutely beautiful shapes that can be made. And this is what's known as a golden era car from the 1950s, a two-tone Cadillac. And of course, it was the ability to make that made driving so attractive. And we're going to have to learn how to do driving a bit differently nowadays. Here's a jet engine. I worked at GE for a while, the biggest jet engine in the world, GE90. You can see that it has a series of what are called blades around here. These suck the air in and then compress it. It's called a compressor. Each blade, you can see here, it's going to rotate and suck the air in, about the size of a person. The air gets compressed, and then there's another row of blades inside, which I can't show you because it's inside, which are called the turbine. The fuel is ignited. The air gets compressed and rushes out like crazy, hits the turbine blades, which drives them around, which then is linked to this, drives this around, and that sucks the air in. That's how the engine works, and it pushes the air out the back, which pushes the aeroplane forwards. And it gets very, very hot in that center where the turbine is. The structure of the nickel alloy, the superalloy it's made from, and by the way, the temperature of the air is about 200 degrees higher than the melting point of the material, which is one of the wonderful technical secrets that we've learned to develop our aero engines. This background here is the nickel, which is relatively soft, and then it's hardened, but it gives it a high temperature strength, and it's hardened with this nickel aluminide here, which is a hard particle, which in a similar way to the steel provides the strength. And then finally, silicon. Here's a beautiful single crystal of silicon, one whole single crystal, incredibly high purity, better than parts per million purity, and it's a 200 millimeter diameter. They now make them 400 and 600 millimeters diameter, and a slice from that, a thin slice cut across it, is shown here with literally hundreds of individual silicon chips here, and each silicon chip, if you look at it, contains thousands and thousands of individual components, and this is one component, which is highly patterned material. This distance here is about 10 or 15 atoms, and each of these different regions has a different composition, slightly doped with different amounts of material in the silicon to give it its functionality. A wonder of modern technology. So that's the history. Now, all of that development, which has been fantastic and wonderful, and massive technological development, has been based around what I call conventional alloying strategy. That means that we nearly always, for our materials, take one main component for the main property and add small amounts of additional alloying elements or components for secondary properties. It's very sensible, and that's why we've done it that way. So, for instance, the nickel alloys for the jet engines, nickel is there for the high temperature resistance, but we had to learn how to add small amounts of aluminium or titanium to give it the strength, and a little bit of chromium to give its corrosion resistance. Secondary properties to the high temperature properties. Similarly, if you want window glass, to take another example, you use silicon oxide, which can be made transparent, but you add a bit of sodium oxide to make it into soda glass, which makes it much easier to manufacture. So you add small amounts of extra alloying additions for secondary properties. In 1979, I began to ask a question, which is, why don't we ever use a multi-component alloying strategy, which is where we mix large number of components in equal or near equal proportions? Why do we never do that? Well, I got told the answer when I said that to my colleagues, and I was at Sussex University, They all said it was a crazy idea. When I spoke to my funding agencies, they said it's a crazy idea. We're not going to give you any money to do something because no one's ever done that. It sounds crazy. When I asked students to work on it, they said, well, we don't want to work on that. Nobody else is doing it. We want to work on some of the hot topics of the day. This was back in the late 70s, early 80s. So that's why we'd never done it. Everyone thought it was crazy. But after working quite hard, well, let me just explain what I mean a little bit more about the idea. So if we want to think about a three-component alloy, three-component material, we depict that on a triangle. And we can think of it as the component A, component B, and component C at the corners of the triangle. It might be nickel here, with adding mixtures of aluminium to give strength and chromium to give corrosion resistance. Well, we add a bit of aluminium, so we move along this. Each point in this triangle represents a different composition. If we add a bit of aluminium, we move along this line. If we add a bit of chromium, we move along this line. If we add a bit of both, we move into this region. All of our materials and alloys, because of this normal alloying strategy, which was never enunciated, but just used, all of our alloys tend to be at the corners of a diagram like this. All our three-component systems are usually at the corners and not right in the middle, the near equiatomic compositions. And if we go to four-component systems with a quaternary system, as depicted in a tetrahedron, it's even less likely that we know anything in the middle of this, what's called a phase diagram. If we go to 5 and 6 components, we know almost nothing about them. Well, we've begun to learn it just recently. That's the basic idea. So I finally persuaded a young man, his name's down here, it's underneath my little picture of myself, but I can't quite get it, but it's Alan Vincent, his name is, Vincent. I persuaded finally a young student, undergraduate student, to do an undergraduate project on this topic. Well, we didn't know quite what to do. We had the idea, but we didn't know quite how to explore this enormous region of unexplored space. You'll see how big it is in a minute. But we thought, well, let's just make up 2 or 3 alloys. So we made up 2 or 3, and this is one. And I show you this one because until very recently, this was the world record in the number of components added in an alloy. This is 20 components with 5% each. And we made that material up, and the truth is it was a mess. And this is the microstructure of it in a microscope, and it consists of lots of different crystals in a big jumble. Not, and perhaps you might say, very interesting. However, we discovered very quickly that it was indeed interesting because this background black area is what's now called the Cantor alloy. We discovered that one of the crystals in this material, one of the crystalline regions, consisted of 5 components: chromium, iron, nickel, cobalt, and manganese in equal proportions in a single phase structure, and it's called a Cantor alloy. So here is the structure. Let me explain it. The Cantor alloy is 5 components, these 5 components in equal proportions. That's 20% of each, a fifth of each. And they exist in a single phase face-centered cubic structure. This is a face-centered cubic structure. It's got an atom at each of the corners of the cube, and it's got an atom at each face center. And if you have, and you can imagine these cubes stacked up in 3 dimensions to produce a physical-sized crystal. Well, if you have pure copper, which is face-centered cubic, every atom, it's like this, and every atom is copper. If you have pure nickel, it's like this, and every atom is nickel. And if you add a little bit of aluminium to nickel, which I already mentioned, you can add maybe, just a little bit, and not the amount we add for the alloy, in the alloys we use in jet engines, but a little bit will what's called dissolve into this face-centered cubic structure. What that means is up to say, let's say 1% could dissolve. It's actually a little bit less than that, but if 1% could dissolve, then 1 in 100 of these atoms at random would be an aluminium atom. And that's called a solid solution. It would be a single phase solution of nickel with a smidgen of aluminium atoms added. And most elements will add in that way. When we add tin to copper, copper is face-centered cubic like this, and up to about 1% of tin, actually, so up to about 1%, 1 in 100 atoms of tin, will just go at random onto this structure. So up to 1% copper, tin, bronze, looks exactly like this. It's a single phase face-centered cubic structure. If we go beyond that, we form a compound, a copper-tin compound. If we go beyond that amount in the nickel-aluminium case, we form a compound. You've already seen it, the nickel alumini, which helps give the strength. If we go beyond it in iron, when we add carbon, we get the cementite, the carbide, which gives it the steel strength. Nobody would have predicted that you could, and nobody did predict, if you added 5 components like that, they would all dissolve into a single phase structure with that structure. What does it mean? It means that there are a fifth of the atoms, a chromium, a fifth of manganese, fifth iron, fifth cobalt, fifth nickel, and they're all distributed on this structure at random. So these at random, a fifth of them are each of those different elements. Nobody would have predicted that. Nobody did predict it. Only nickel of those has this structure in its pure form. So it was a complete surprise. And it turns out that this material has incredible properties. Now, it's not just one Cantor alloy. It's literally hundreds of thousands of Cantor alloys. It's not just one, because you can add other components into it and make the alloy range is enormous that you can have, which has this single face-centered cubic structure. In the middle of that 5-component phase space, the tetrahedron, or the next stage up, because it's got to be 5 components, in the middle there's an enormous patch of region which has a face-centered cubic structure like this, which nobody predicted. And people are now beginning to look at the properties, and they've discovered that they've got great properties. This is the great properties they have. So this is what happens when you put a stress on a material. If you put a stress on a material, then that's the stress, the level of stress, and this is the amount that the material strains, the amount that it stretches. And initially, it just stretches elastically, and then it begins to deform more with a permanent set, and that's when it curves over like this. And this is the initial Cantor, original Cantor alloy, and this is one of the modified Cantor alloys. Now, ceramics and things like rocks and ceramics materials don't show this ability to deform like this, to change their shape. They just stretch, but they go up to quite high levels of stress, and then they just fracture. Metals, pure copper, pure gold, and so on, pure nickel, are soft. They don't go very high up here, and then they deform a lot. That's why you can beat gold into gold leaf and turn almost pure iron into those beautiful cars that I showed you. The Cantor alloy has an amazing mixture of, my pointer stopped there. There we go. And it has a tremendous mix of both high strength, it goes up to high levels on this axis, and ability to deform. It deforms the best part of 50 to 100%, but at the same time it has strengths up into the half a gigapascal to a gigapascal level. This is shown more in this so-called Ashby map, which is the same sort of thing really. On the bottom axis you've got the strength, and on the upper axis you've got the fracture. A crack from propagating. This shows ceramics are here. They've got pretty high strengths, but not very good resistance to fracture. High strength metals are at the upper end of these different metal regions. They've also got high strengths, and they've got better fracture resistance, which is why they're used for fracture resistant purposes. The highest strength steels you can see, and then the high entropy multi-component alloys are up here. They have the best combination of these properties yet discovered. So that's why people are interested. Now, Professors Murty, Yeh, and Ranganathan, you can see down in the bottom right-hand corner. So let me finish the story. Mr. Vincent, he did his work, and in 1917, he did it in 1981, and he got his degree. But he wasn't a very good scientist, and he went off to get a job in management. And the work he'd done showed us the answer, but it wasn't good enough to publish. It wasn't until 20 years later I persuaded another undergraduate student at Oxford University to repeat the experiments, and he got the same results. But he also went off, because I struggled to get any good students to want to study this behavior. And finally, I asked my postdoc at that time, Isaac Chang, who's now a professor at Brunel, to repeat the work and do it well so we could publish it. We had to have good results so we could publish it, otherwise it wouldn't go through the peer review. So finally he did, and we published in 2004. our paper, which is now quite well known, and it bombed. Nobody referred to this paper for the next 2 or 3 years. And I was off running universities, as Dame Mary's already said, at York and then at Bradford. And I was surprised to discover around about 2010, 2011, that people were beginning to work on it. They'd finally picked up on it, mainly because of Professor Ye, one of the 3 people that produced the book I just mentioned. Murti Ye and Ranganathan down in the bottom right-hand corner there. So Jingwei Ye in Taiwan began to study the same thing, and it began to get known, and it began to take off in 2010. So in the 2 or 3 years after our paper was published in 2004, there were no citations. Now there are literally thousands of citations a year. There are literally thousands of scientists working on these materials. There are multi-million-dollar programs in almost every developed country. And it's just taken off like crazy. It's one of the reasons when I stopped running universities, I decided to go back to being a scientist and work on this a bit more. And in 2014, they published their first book on this topic. And they showed, these are the Cantor alloys they showed, 3 pages of them, 1, 2, 3. I'm not going to go through them all. They've just published an update about a year ago, and there's about 3 times as many now. That's how many different Cantor alloys there are. Dan Miracle, who is Dr. Miracle, who is the head of US Army research in Ohio, the Army labs in Ohio, Air Force labs in Ohio, published a review recently which said that this multi-component approach has already led to 8 new categories of materials. The Cantor alloys are just one of those new categories. There are literally hundreds and hundreds of thousands, probably millions of Cantor alloys. And there are 8 other categories, similarly with hundreds of thousands and millions yet to be explored materials of potential interest. And there are almost certainly lots of other exciting new categories of materials to be found. As Dr. Miracle said, we've only just scratched the surface, but we are finding an amazing array of new materials. So let's work out how many materials there are. So if you have C components, if you start with C different starting materials to mix, and if you decide that 2 different materials are counted as different if they differ by X%, so if we consider how many different materials could we make out of our C components if by changing the composition for each of them by X% meant we move from one material to another, the answer is the number of materials is shown here. It's this combinatorial equation. It's actually school maths, but I won't bore you with the details. But that is the answer. That's how many different materials there are. Well, how many components can we use? Well, there's 120 elements or thereabouts, but a lot of those are toxic or radioactive. So probably we could use 80, but let's be really conservative and say we can use 60, which are the well-known metals and non-metals like silicon. And now, what about the discrimination between different materials? Well, most materials are specified to 0.1 or 0.01%. Some we've already seen, the highest strength steels and the highest and the most important electrical semiconductors are specified to parts per million. And it's a very poor quality material that's specified to 1%. So we'll take X as 0.1%. Pretty conservative estimate, because normally we like to stick to 0.01%. The total number of materials, if C is 60 and X is 0.1%, is 10 to the 100, which is a Google. I believe it's why Google is called Google, but it's obviously spelt different. But it's a very, very big number. 10 to the 100 is an enormous number, 10 multiplied by itself 100 times. For comparison, they're estimated to be 10 to the 66 atoms in the galaxy and 10 to the 80 atoms in the universe. There are more potential materials we could make than there are atoms in the universe. So I always tell material scientists that they're in the right business because there's an awful lot of materials to study. So this is my definition of gazillions. How many have we actually looked at because of our conservative alloying strategy? Well, we don't know as many as the total number of 3-component systems. We don't know all the 3-component systems, and we know very few beyond 3 components. So I estimate that this is the number of 3-component systems that there are, about 1 trillion. So we've discovered a tiny fraction, and we're beginning now to explore this vast, vast array of multi-component phase space, multi-component material space. And as I say, we've discovered 8 major categories of materials, one of which are the Cantor alloys, which have some of the properties I've mentioned. Now, I'm going to say a little bit more about the Cantor alloys as the last, my last section, just to make some sort of interesting points. So if we think about, so this is just the Cantor alloys now, not those other potential multi-component systems. So this is a depiction of what a 5-component system might look like, or a 10-component system. They're not very accurate because, for reasons that you'll see, but most notably, first of all, they're not on a real crystal structure. This is just a square lattice, and this is the same thing as square lattice. But it gives you the important idea. The important idea is this: if every atom in the lattice is copper, then the environment at every place is the same. That's the characteristic of a crystal. If every molecule is silicon oxide, then the environment in quartz is the same at every point in the crystal. If the environment is, if you take nickel, then every atom is nickel. So the environment, the local structure, the local properties are the same everywhere. In the Cantor alloy, that just isn't true. So not only is it because we've got 5 components, that makes things a bit more complicated, but if you look, each A component is surrounded by, because it's at random, is surrounded by a different structure of nearby atoms. And if you want to work out how many there are in a face-centered cubic structure, like the original Cantor alloy, with 5 components, it turns out there are 20 trillion different local environments. So instead of having face-centered cubic copper, where every single local copper atom is exactly equivalent to not every other one, we now have a material where there are 20 trillion different local environments. And if we add another component, it goes up to about 300 million. And if we take into account not just the nearest neighbours, which sometimes are important to the properties, it goes up to literally enormous numbers. So I won't go through the calculation, but you can see that the properties of the material are incredibly variable from one point to another inside the material. This leads to a load of important and interesting properties. I'm going to show you 2. So let me first of all just put a bit of flesh on the bones of that. These are the first 5 elements here are the 5 elements of the Cantor alloy. We won't talk about the other 2. Their radii are given there, called so-called Goldschmidt radii. The rough size difference between them is 3 picometers. It's about 2 to 2.5% is the difference in size between the different places. So what that means is that there's about a 2% stretch in the lattice locally. That's quite high forces locally. 2% strain in a material leads to quite high forces. So the lattice not only has all sorts of different environments, it's got different stretches and distortions inside it. This is proved here by some synchrotron X-ray diffraction experiments which came up with the answer of 4.8 picometers size variations in the material, and neutron diffraction experiments which showed 2 picometers. So roughly it's in agreement with what we would calculate by a rather naive calculation I've just given you. Well, this leads to 2 important property effects, at least to many others, but I'm going to show you 2. The first one is the resistance to degradation of the material. Now, this depends upon how fast the atoms can move around in the material. We measure this by something called the diffusion coefficient D, and we normally plot D as a function of temperature on a D versus reciprocal temperature plot. So high temperatures on the left, low temperatures on the right. This shows the speed at which nickel atoms move in the Cantor alloy, which is at the bottom, actually 2 Cantor alloys, the original one and the modified one, and in some comparison face-centered cubic materials like pure nickel and a nickel superalloy. And you can see that the speed at which the atoms move at any given temperature is about an order of magnitude slower. So the atoms move more slowly. It's not surprising. The lattice is incredibly variable and incredibly distorted. So if atoms are going to move around, they've got to push their way through a much more complicated set of environments, and they find it very difficult to do it. So that means that they're very resistant to degradation as a material, whether they're exposed to high temperature, or they're exposed to corrosion, or they're exposed to radiation damage. And the Cantor alloys are being looked at actively as temperature resistant, radiation resistant, and corrosion resistant materials for just that reason. Now, I've already mentioned the strength and the ductility, or the fracture resistance, which is related to the ductility, the ability for the material to deform. And this depends on things, lines like this black line here, which are called dislocations, which are a defect in the crystal. So if you have a face-centered cubic crystal, as I've shown you, there will be lines of defects. And the reason you get the deformation behavior, the reason that metals can be plastic, the reason they can resist fracture, is because under enough stress, these dislocations begin to move. But the stress isn't very high, which is why they're not very strong. And you have to try and strengthen them. Well, in the case of the Cantor alloy, every single atom is resisting the motion of these defects, just like it resisted the individual atoms themselves moving. That is why, although they're still very, very enormous, got enormous amounts of ability to resist fracture and be deformed very easily, it's why they nevertheless have very high strength, because the dislocations are very hard to move. The theory for this is given in this equation, which I won't bore you with in any detail, but that is the theory of what all those atoms should show. It's taken a while for us to get to the point where we could have a good theory of it. And this shows the comparison between the experiment black and the theory red for the Cantor alloy itself, and for a modified, slightly reduced Cantor alloy here. So you can see that that explanation in broad terms gives good results. So because of that, the Cantor alloys are being studied. They've already been demonstrated to have outstanding cryogenic properties at low temperatures. They're being studied for high temperature materials. They're being studied as corrosion resistant and radiation damage resistant materials. Some of the other multi-component systems, not Cantor alloys, are being studied to try and find new materials, things like solar energy conversion, things like high temperature superconductors, all the wonderful new materials which we have discovered already. People are looking for improving them and finding ones with new functionalities in this amazingly broad range, this vast array of multi-component material space. And Dame Mary mentioned that I've recently, with my colleagues at Brunel, won a major UK government research grant to use the same materials to look at recycling. The problem with recycling at the moment, metals contribute, and metal-based products contribute about 12 to 15% of all greenhouse gases and all pollution and all use of energy. Metals are pretty well recycled. About 50% of all metals are recycled, but we don't recycle them very well. And the reason, and 50% of them aren't recycled, and the ones that are recycled aren't recycled well, in the sense that they're taken back to the smelter, usually. We treat them as if they were just all we dug up from the ground, and we go back and we make new pure metals, and then we realloy them. If you could just melt them and you reuse them, that would be much, much better. Most of the energy use is in the shaping of the metal, not in its original smelting. So if we want to reduce carbon emissions, if we want to reduce greenhouse gases, we want to reduce pollution, we want to just not take it back to the smelter. We want to take even the 50% we recycle, we want to just be able to remelt them directly into new products or similar products. But to do that, we've got refined, specialized materials and alloys for every single thing we use. So the problem is with recycling is sorting out all the different alloys, which are so highly specialized and contain so many different components. So what we believe is that if we can find alloys which have got lots of components in them, then they'll be perfectly capable of absorbing other components. And there's some evidence that that's the case. So that's recycling. Now I'm going to finish with 3 slides, which I discovered quite by accident because when I was Vice Chancellor at the University of York. And I had a head of the chemistry department, a man called Paul Walton, a very able chemist who studied metals in the body. And he used to give he was a wonderful lecturer, and he gave great lectures to school children and used to go around. He was very much in demand. And I discovered he was using 3 slides, which I like very much, and make the point about multi-component materials. So he would show school children, maybe aged, I don't know, 13, 14, so early sort of high school, mid-level high school students, not sixth form, not those that are graduating from high school. And he'd show them a slide like this, and he'd say, does anybody know what material this is? And of course, at that age, most of them knew, and they'd all put their hands up and they'd say, sir, it's carbon. And he'd say, yes, you're right, it's carbon. Then he'd show them this picture, this slide, and he'd say, here's a harder one. Does anyone know what this material is? And of course, at age 12, 13, 14, they've probably done a little bit of chemistry again, they put their hands up and they say, sir, yes, we know. It's water. It's a liquid material, but it's still a material. It's water. Then he'd show them this one and say, so what do you think this is? And I've given the game away for you. He didn't, because they wouldn't know. It's the secret of life. This is the composition of the human body. Your body, my body, everybody's body. It's the same. Actually, I think it's the same for all mammals. It's almost the same for all mammals. And it's incredibly specific. So to take the most obvious example down here at the bottom, selenium, that represents, because this isn't out of 100, this isn't percent, there's 650,000 carbon atoms, and there's only 0.000 whatever it is, one selenium atom. It's about 1 in a trillion atoms is selenium in our body. And if we have 2 in a trillion, 2 atoms out of a trillion of selenium, we die. And if we have only 1 atom in 2 trillion, we die. We have to have that atom of selenium in our body, and we have to have the 10 atoms of cobalt in a trillion in our body, and not 20 and not 3. This is an incredibly precise composition. The human body is an amazing object in many ways, and even in chemical terms, it's amazing. So this is a point in the middle of that 60-component material space that I have talked to you about. There are many, many other wonderful, wonderful points and regions, whole regions like the Cantor alloys, yet to be found. We have discovered a few of them, but there are literally thousands and thousands of wonderful, well, actually millions and trillions and gazillions of wonderful new materials yet to discover. So my conclusions are the same as my starting point, with one addition. Human history, I hope I've shown you, is the history of the development of new materials. Materials are made up by mixing other materials, they're alloys. There are literally gazillions of them, and there are literally gazillions of them yet to be found. Thanks very much.
Thank you to you, Brian. It was very nice and interesting. Maybe have some problems in speaking. So whoever would like to make any kind of question, remark, I would appreciate of any you, both professors, students, or what else. I think the whole story is nice and impressive, and is something that we appreciate. Is something that very special, very in a way unusual. So someone had the courage to explore new fields, and the field is really huge, much more huge than one would expect. And so it was very nice for me. I don't know if you have any specific more question. Is something that also I would like to explore, from one side. But I think it is a very nice story about science, about materials and metals, for sure. And it's something that one should know, because you have to fancy something that's different, and then to explore, and then there is something. So I'm really pleased to have you here and have this lecture from you. Okay.
Okay.
Okay. So now
let me add one other thing.
Please.
I often finish this talk, and I forgot to say it. I like to say to, I know there's a number of students in the audience. The world is fantastically full of fantastically interesting things which science can discover. And I thought that when I was a young man, but it's way beyond what I thought when I was a young man. I thought science had discovered quite a lot of things, and we're going to discover a lot more. But we're a million miles from discovering things. And materials is one area, and there are literally gazillions of materials. So I say to scientists, be bold, be adventurous, go and find things. There's wonderful, wonderful things to find. And the biggest drag on people, particularly young scientists, is that they get a bit nervous and they think they want to study what everyone else is studying at the moment instead of going and finding new things. Be an explorer. Science started with exploration. I'm just reading a book about how the initial scientific revolution really stemmed from people beginning to explore the world, and that gave scientists confidence to try and explore the world of science. So it's about exploration, and there's a lot to explore.
Yes, for sure. I had the pleasure to attend some years ago in Cambridge a conference organized by Professor Harry Badesha, which I hope is still there. And the conference was Adventures in the Physical Metallurgy of Steel. So I think that you should try to explore something which is not explored. So precisely what you have been talking about, and also what was this conference and other activities about, is something that must fascinate especially young people, but not only young people, truly. And this is the right attitude to do something which is new. So this is my point of view. And I would like to thank you again. And usually, I know my students, normally the students of this part of Italy, they are not the usual Italian guys that one would expect. So they are a little bit more shy. So I wouldn't expect that they would make questions on or whatever. But I would like to have them. Ragazzi, sicuro che non volete fare una domanda al professore, è una buona occasione. But if there are no problems, it's I know my classrooms in this part of Italy, which is northern Italy, it's not southern Italy, where the people is much more communicative. And it was really a big pleasure. We are organizing this meeting in a couple of weeks. I will have Jean-Pierre Birat speaking about the evolution for green steels. And so we are trying to keep, in this very strange situation, we are trying to have connection from the outside world, which was very successful. I'm really pleased to have this very important scientist from United Kingdom. So it was a really very great experience from myself. I do hope that also my students appreciate it. I would also like to thank also my friend Jeremy Paul, who is also a professor who has joined us. And for the moment, Harry, would you like to say a word more? If you, yeah, I would be so pleased. Please, Harry.
Yeah. So, Brian, thank you very, very much, and also Professor Miani. There are two things. First of all, I know that this is being recorded, and I would like, if possible, I would like a copy of the video to put on my YouTube channel, which is...
would be very nice. Your YouTube channel is fantastic, and it's for students and professors and of any age, and it's very, very useful. So we will try to have it, and that for sure I will send to you if you agree. Of course, Professor Cantor as well would be very nice for if you. So we can expand even to more people. YouTube is sometimes difficult, but sometimes it gives very, very, very good things. I have been using a lot. Unfortunately, he's not any longer with us. The lesson of Professor Bruno de Coman to diffuse it to my students. So from your own channel, and I think that and so this is a kind of way of remembering him. And so I think you have plenty of useful materials, Professor Badesha, to give. With the generous spirit to everyone in the world, not only students in Europe, but students all over the world. And I think that also once more to have this clear situation about this, your lesson, Professor Cantor, is easy to grasp even by not specialists. So this is the right point to start to infuse enthusiasm, to infuse interest in especially in young people, in students. So it has been a very, very nice experience. Okay.
The second.
Just say, Harry. Let me just say, of course, in principle, I'm very happy with it. I just hope I wasn't too stuttering at times. But in principle, I'm very happy, of course. And
but Brian,
in fact, I'm pleased that you want to do it. It's very kind.
Let me ask you a provocative question. Okay?
Go on.
So, you know, these days we have huge amounts of money for research and so on. And even if you look at Dan's review, it's full of promises. We haven't actually got to a stage in high entropy alloys where people are looking at scaling up and looking at a particular application. And I think that's where the focus needs to be. And maybe your project at Brunel is about this. But
Well,
as
yeah,
far
it's a very good point.
there is only one application so far, which is on making a brazing alloy.
Yeah. No, it's a very good point, in my experience, you may have different experience, but I've worked on a variety of different areas, not just this area, of course, where new materials are being developed. And it's often said that the time it takes for a new material to actually end up being implemented, that's one new material. And I think there are many new materials being looked at in this multi-component phase space. But for one new material, one new idea, it typically takes 20 to 30 years before a real application is used. And even which is the best application isn't normally known. In fact, it normally takes a couple of economic cycles, a couple of cycles of excitement of studying things, because people go off and study lots of things and find lots of things, but don't quite get it right. And they need sometimes to have a pause and then come back renewed with fresh ideas before they can make it happen. So you're right, it's not happening immediately, but you know, the multi-million-pound programs have only started in the last few years, so it's still, I would say, early days. Most of the work has been on Cantor alloys, and it'd be interesting to see whether something does transpire from that. But there are other alloys and other materials being looked at too. The way I always think about it is this: we've just had the most wonderful success for science ever. I thought the coronavirus problem was going to bring scientists into disrepute, because we had a lot of people predicting how the epidemic would roll out, and of course that's an incredibly difficult part of science, epidemiology, which is full of lots of lack of understanding. So it was initially wrong predictions were being made, and it looked like science might be getting a bad name. But the development of the vaccines has been an absolute triumph, and it's brilliant. And what it shows is that if we put money into something to discover a new material, we will discover a new material. And the reason we will do it is because there really are materials out there. And the reason there are materials out there, I know that and understand it, is because multi-component phase space, multi-component material space is just so incredibly large.
But you know, you're missing my point, Brian. You're missing my point. Yeah, I think that there is enough money, but people are not focusing on the right problem in high entropy alloys, which is actually to scale up and to look at an application, because once you look at an application, you have to satisfy more than just one property. And the vast majority of high entropy alloy papers focus on just one or two properties, whereas you need a combination of properties to actually produce a component. And that actually is very challenging for research. So it's not something taking away from basic research, but if you focus on a bank of properties that's needed for a particular component, then you do remarkably interesting research.
Yeah, but I think you're missing. I was not really dealing with that. I agree. So in that sense, I was missing your point, but I wasn't really missing it because I was really trying to make a different point in Cantor. So the point I want to make is this: when I was vice chancellor at Bradford and at York, and when I was head of science at Oxford, I got invited to a lot of policy meetings, which most people, now I'm back at being a working scientist, I don't go to those things. So, there was a regular question at the big policy events, the things that involve chief scientists and chief technologists in companies and ministers of science, and the big. I went to a number of these regularly, to a number of these sort of conferences and meetings, and one of the regular questions that comes up is, are we running out of materials? Most people, even quite well, sensibly, educated, scientific people, have this idea that we're running out of materials. The point I want to make is this: if we focus onto a material that we want, we will be able to find a material. Now, in the past, we did that relatively tentatively when we did it. The whole point about multi-component phase space is not really answering your point, I agree, but it's a counterpoint which says that we should think tangentially to that point. The point is that we've expanded our capability of thinking about where we might look for new materials. So if we have a material need, then we've got a much bigger patch we can look for. And people were being people have been very tentative when they look to improve high temperature superconductors, or they look to improve solar energy materials. They start with the ones we know and try and tweak them up, rather than looking for more innovative solutions. And what I'm saying is that the real payoff in multi-component phase space will come with that. But I agree with you completely that once you've decided on a particular material for a particular kind of material for a particular application, getting it to the point of application is incredibly challenging. Most of my scientific career was working on applied materials, and that I love the fact that you had to meet lots and lots of different complicated specifications and requirements, and that is very, very challenging. Yes, of course. And I'm not saying that Cantor alloys are solving all the problems in the world. I agree.
Thank you very much. Thank you very much for a fascinating talk. Okay.
Yeah, thanks for your comments, Harry.
Yeah. So I have a final question, which is, of course, I believe that not necessarily by myself, something related to the Kalfat development of Cantor alloys could be done quite simply, because in my would say naive way, I have developed some open databases, for instance, for copper alloys. Yeah. I don't think it would be that difficult, maybe someone more expert than I am, to grasp, to pick up, because after all, you have to model a liquid phase, you have to develop an FCC phase, and so the interactions, and so at least for 5, 6, or even more, but it should be not impossible at all from a practical point of view if you use it open. So I am fond of Kalfat as long as you can use with open databases. I'm not the one expert, but I can grasp and pick up and collect other databases. So once you have the data, maybe you can develop things. It could be useful, for instance, for study. If you have to process some alloys to have ideas of the liquidus, of the solid, let's say, room temperature properties. Of course, it wouldn't tell the truth, because the truth, it is the experiment, is not the modeling, but for this issue. But I think it could help. So maybe it would be nice in the future to pick up some guys working with the Kalfat, possibly enough professional, but not too much linked to the commercial world. And so I think because there are already some commercial high entropy alloys, and nowadays I read a couple of papers recently for your lecture actually, and some people working in Aachen, but basically, and they have developed something that also related to steel, let's say to lightweight steel, so the kappa phase in steels and so on. So I think something can be done, but unfortunately the database is not open. So I will try to model something and to do very, very simple things, maybe with my students, in order to have some ideas.
Let me give you an answer, Professor.
Please.
Right. And like many questions, the answer is yes and no. Mm-hmm. So of course, the Kalfat and thermodynamic calculations is a great tool for investigating materials and trying to make some predictions as well, both for supporting experiments and for suggesting experiments. So is first principles calculations. I know a lot of people say to me that we should use this modeling capability. So in one sense, the answer is of course, and people are doing it. People are using Kalfat type calculations, and they're developing new methods, based on big data type calculations as well. So to take existing data and try and make predictions, to try and find patterns in what's already been discovered, to give new grooves as to how one could begin to explore this in massive amount of space. But there's a problem. There is a problem, and it's a very central problem, which I think is unsolvable. And it's why exploration is so important. It's why people didn't understand about mechanics until they started exploring and believing that it was worth even trying to do it. So let me explain the problem very quickly. Our knowledge of materials is all based, not quite now because of the development of this field, but still almost all based upon individual components with one or two additions. And our theories are based on that too. you know, and all of our theories, whether it's fundamental calculations or whether it's thermodynamic calculations, and we cannot easily extrapolate very far outside of the experimental database, as you've rightly said. So the problem is we don't have the experimental database with the calculations that they work well. Of course they work well. Where we've now beginning to build in little patches of multi-component phase space where we built up data, we can begin to use those with some accuracy. And occasionally the big data type attempts to interpolate and even extrapolate a little bit beyond what we know work. But you know, there are new things going on. The cross terms, when most of our explanations rely on dilute solution approximations.
Yep.
And dilute solution approximations don't work. There are what you call cross terms, where the effect of one solute or one alloying element on another alloying element gives you you know, non-linear behavior, and gives you means you can't just add up the effects of those two. So unless you've done the experiments, the databases aren't right. So, you know, the truth is we have to kind of do a bit of both. It's like most science. So the more I think about science, I realize that, you know, I'm an experimental scientist. I tend to often to say the theoreticians get too much kudos and the experimentalists don't get enough. But the truth is we need both. We need every single tool we can to discover things about the world. And we need to explore and experimentally. It's not really trial and error because it's sort of sensible. You know, it's guided trial and error. And we also need to use our theories to give indications. And it's when the two begin to cohere and work well that we really make progress. So yes, by all means do it. But it's not actually the solution to what's out there in this vast sea of unknowns.
Sure.
So anyway, let me just say thank you very much for inviting me.
Yeah, to you. It was great for me. It was great for this small town having you from, and you estimated professors, and it was very, very, very important experience for me. All the best, and so all the best also to my students, and stay safe this difficult moment, and all the best. Bye.
Bye.
Thank you.
Bye. Bene ragazzi, vi saluto, spero che siate riusciti a non sacrificare troppo della vostra pausa pranzo, e per me è stata un'esperienza importante. Abbiamo avuto comunque dei docenti di primissimo livello a livello mondiale. Il professore Ribadescia è il più importante professore per quello che riguarda la metallurgia degli acciai al mondo, quindi siamo stati lieti di averli qua. Vi auguro buona giornata e vi ringrazio per la partecipazione. Arrivederci.
Grazie, arrivederci.
Grazie per aver seguito